Yeah, thank you everybody, and thank you for coming to the our monthly fourth seminar. And my name is Kyusei Tsuno, and I will be leading the seminar and the discussion. And today, I'm very happy that we fourth invites Professor Asmaa Boujibar at Western Washington University. But before starting the seminar, there is a few updates. And so FOSS has several SNS, and we have an YouTube channel, and after this talk is recorded, and after the talk, we will upload this seminar. And we also have the X, Instagram, and LinkedIn. So please subscribe, and you may receive an update from FOSS. And I think 2 weeks later, we have another monthly FOSS seminar. Professor Damanvir Greval will be talking. So, okay, I'll say a brief biography of Asmaa. So the Asmaa Boujibar, Dr. Asmaa Boujibar is a planetary chemist, and based on the experimental petrology and the geochemistry. So she received a PhD at France, University Clermont Auvergne. And after that, she came to the US, and she did some postdoc at the NASA Johnson Space Center and Carnegie Institute of Washington. And now she's an assistant professor here. So she will be talking about a mantle chemistry of the Mercury. So Asmaa, you can start. But can you upload your slide?
Sorry, can you?
Do you have the PowerPoint slide?
Yes, my slides here. I'm going to share them.
Can you share?
Yeah. Okay.
Okay, it's good. The rest of the time is yours.
Okay, I thank you very much for inviting me to give this talk. I just wanted to say that I have to teach at 1, so I'm going to leave at around 12:55. Okay, so in this talk, I'm going to talk about Mercury's differentiation.
Asmaa, sorry, it looks like we see the I think presenter. This is not actually not the whole slide. So
yeah, that is very strange. Let's see here. Stop sharing. What about now?
Yes, this is fine.
Okay. Perfect. Okay, so I'm going to talk about Mercury's differentiation in the context of the solar system formation and differentiation of the planets and chemistry of the inner solar system. So, and the two main questions that I'm going to address here are there any gradients in volatiles and redox conditions in the inner solar system? And how do rocky planets and meteorites compare in chemical composition? So I'm going to talk about the structure of rocky planets, and distribution of heat-producing elements, uranium, thorium, potassium in Mercury's mantle. And then I'm going to talk about Mercury's mantle composition and how they compare to enstatite chondrites, as well as other planetary building blocks within the inner solar system. Okay, so the solar system formed with this giant cloud of gas and dust, and so as it actually rotates and shrinks, things start to rotate faster and faster, and then we start forming a disk with planetesimals that that aggregate and start forming larger and larger bodies. And at the end, we start having a solar system with planets and small planetesimals that actually come from bodies that didn't accrete to form the larger planets. And so the questions here I'm going to address are, do we have any general trends in the inner solar system where we have planets like Earth, Venus, Mars, and Mercury? So if we look at the oxidation state in the inner solar system, we can see that through large-scale features, for example, FeO concentration in the mantle. And so we see that FeO in the mantle of rocky planets increase with the heliocentric distance. And here I have Vesta as well, which is an asteroid between Mars and Jupiter. And so, yeah, you can see that FeO increases with heliocentric distance. And at the same time, the fraction of the iron core decreases with the heliocentric distance, with Mercury having a very large core and Mars a smaller core than for Earth and Venus. And so this shows that there's more iron metal close to the sun and more iron oxide away from the sun. So this shows that we have FeO over iron that increases with the heliocentric distance, and that actually just shows that broadly planetary bodies are more and more oxidized as you get further and further away from the sun. And so now we can also look at primitive meteorites, chondrites. So chondrites, compared to other differentiated meteorites, they actually come from smaller bodies that didn't melt completely to form a core and mantle. And so we can have a really nice record of the early solar system formation processes by looking at these chondrites. And so we can also look at the redox state of iron within these chondrites, and that's shown with this diagram, the Urea-Craig diagram. And so in the y-axis here, you have metal and sulfide, and the x, you have FeO concentration and silicate. So kind of the same than the diagram we saw earlier for planets. And so both here normalized to silica. And yeah, one thing that we see is here I report the main families of chondrites. We see that carbonaceous chondrites have most of their iron present in the oxide phase, versus enstatite chondrites have almost all of their iron present in the metal and sulfide phase and almost none as an iron oxide. So we do have different oxidation states within the chondrites, so the very early bodies that form in the solar system. And so now these chondrites and meteorites come mainly from the main asteroid belt and asteroids that are nearby. So in here, I'm showing a map for where these bodies come from. And so you see here that this map covers distances between Mars and Jupiter, with the main asteroid belt shown by these central ones here. And so what we see is a distribution of the types of asteroids. And so because asteroids have been classified based on the reflected light, by comparing with the same kind of spectra from meteorites on Earth, we can actually have an idea of what kind of meteorite would actually come from these asteroids. And so this map actually saw these spectra, and these authors here, they provided this map that shows the distribution of these asteroids around the main asteroid belt. And one thing that we see is that further away, closer to Jupiter, we see more carbonaceous chondrites. You see the dark colored here, black, blue, purple. And closer to Mars, we see asteroids that are like ordinary chondrites, but also enstatite chondrites, type E, type M asteroids, and as well as some carbonaceous chondrites, but less than the regions close to Jupiter. And so this shows that we do have mixing because we see kind of everything everywhere, but we have a general trend that still persists in these asteroids. And for example, enstatite chondrites are mostly found here very close to Mars. Yeah, so we might have still a remnant of this gradient of oxidation state within asteroids distribution in this area. So now if I use the same Craig diagram, so you remember we have enstatite chondrites here close to FeO iron oxide very low and carbonaceous with the iron oxide. So now I can report rocky planets here, and you see that Earth, Mars, and asteroid Vesta here, they don't really match any of these chondrites, but we do see again this gradient of oxidation state. Okay, so we might have a random oxidation state in the inner solar system. So what about volatiles? So within the inner solar system and the solar system in general, when it formed, we had hotter areas close to the sun and cooler further from the sun. And this actually led to the distribution of volatiles in the solar system due to volatiles actually in the gaseous form where the solar system is hotter, close to the sun, and volatiles could condense away from the sun. And with this solar winds, strong solar winds at the early formation of the solar system, so a lot of these volatiles that were in the gas form were stripped away from the inner part of the solar system. And this is how broadly we understand the presence of giant and icy gases away in this outer solar system and rocky planets closer. So this is just due to the fact that these highly volatile elements were more enriched in the outer regions. And so the question here is, do we have any other gradient here? For example, do we have a richer area here in the outer part of the inner solar system? Do we have an enrichment in moderately volatile elements and enrichment in refractory elements close to the sun? And by moderately volatile and highly volatile refractory elements, I mean hydrogen, carbon, nitrogen, things like that. They're considered as highly volatile elements, so they condense at very low temperature. And moderately volatiles are those that condense at slightly higher temperature, like sodium, potassium, sulfur. And refractory elements are elements like aluminum, calcium, titanium, uranium, thorium. These condense at very high temperatures. So, okay, so do we have an enrichment in these refractory elements close to the sun? And so the best way to answer this question is to look at Mercury, which is the closest to the sun, right? And so here I'm showing you here a diagram where we see potassium over thorium ratio. So potassium is this moderately volatile element. Thorium is a refractory element, and so we often look at the ratio between these two to assess this volatile enrichment, because these two elements behave in a similar way when there's a magmatic differentiation. So if you look at the surface potassium thorium ratio, it would reflect the bulk planet ratio. So it's really practical to look at this one to actually tell about volatile depletion. And so here it is reported as a function of the distance from the sun. And you can see that Mars has a higher ratio than Earth and Venus. And so because of this gradient and also the presence of icy and giant gaseous planets in the outer solar system, prior to the mission Messenger that visited Mercury, we were expecting that Mercury would have a lower ratio than all these planets. So we'd have like a trend that looks like this. But actually Messenger went there and it had a gamma ray spectrometer that was able to measure this ratio. And the ratio we measured was actually as high as Mars. And so that was very different than what we were expecting. And so actually this was suggesting that actually we don't have a gradient of volatile elements, and we might just have some kind of random distribution within these planets. And so now the thing with Mercury is that it is very reduced. It has this really large core. And the question that we can ask is whether actually we have some of these elements trapped in the core and distributed in a very different way than other solar systems, so that actually this hypothesis that I talked about, where potassium and thorium do not fractionate during magmatic differentiation, might not be valid for Mercury because of these very reducing conditions, low oxygen fugacity and large core, and also presence of sulfur. So to test that, we actually conducted experiments at high pressure and high temperature to simulate core formation and see how these elements distribute between the different phases that we have, metal, sulfide, and silicates. So we do this by mixing different powders of metals, sulfides, and oxides, and having that powder, putting that, packing it in the capsule, and then taking the sample to high pressures and temperatures using a piston cylinder or multi-anvil press. And then we have samples that look like this with the metal and silicate included in the capsules. And so these allow to model core formation. And so at low oxygen fugacity, we actually have a lot of silicon that can enter the metal. So the metal is not just pure iron or iron nickel, but it has also a lot of silicon. You can see with this diagram here, as you decrease the oxygen fugacity, you increase the silicon in metal. And this oxygen fugacity is expressed here as relative to IW buffer, this iron volatile buffer, FeO. And so it's just a difference in oxygen fugacity of the sample and the oxygen fugacity of the buffer, iron volatile buffer, are the same conditions. And so it can be calculated with concentration of FeO over iron. And so this is only possible when we have enough of this FeO measurable in the silicate. The problem is that as you go to more and more reducing conditions, you have less and less FeO in the silicate. So when we reach some concentration that is lower than that, like here we consider 0.1 mole percent FeO, we use another equilibrium, the redox of silica, because we do have a lot of silicon in the metal. And so by using this equilibrium here, we can calculate oxygen fugacity for those very reduced samples. So anyway, so here we show that at low FO2, we have a lot of silicon in the metal. And also, when we have sulfur in the system, especially we have significant sulfur, we start forming two liquids, two iron-rich liquids, one with the FeS, one FeSi, and this boundary here, so it's reported in this ternary diagram. So this limit here, this boundary where we have one liquid and two liquids, actually varies with pressure. And so here it is for the pressure of Mercury's core mantle differentiation. So if we are in this field, if the starting metallic composition, metal and sulfide is within the left corner here, we would have one liquid. If it's in the rest of the diagram, we have two liquids. And so here I also reported in purple the composition of chondrites, because we know chondrites have a range of sulfur, so we can better constrain here where would planet sit in this diagram here. So it would be in this purple diagram. And since here we show that when you decrease oxygen fugacity, you increase silicon in the metal, the more reducing, the more up in this diagram we're going to be. So the more likely we are to form iron sulfide, right? And so in the chondritic sulfur ranges and at low oxygen fugacity, we are likely to have sulfides present as well. And so we would need to consider the sulfides in our models. And so this is a sketch just showing how it is. Like we have some models where we just have iron core, iron silicon nickel, and silicate mantle and crust. And we also consider another model where we have, in addition to that, an iron sulfide. And so, yeah, if it's really iron rich, it would have a density intermediate between core and mantle, so it would sit between the core and mantle. But later in the talk, I'll show that this can be more complicated. Okay, so let's go back to this question about potassium, uranium, and thorium. So how are they distributed within the interior of the planet? And so we conducted experiments, high pressure and high temperature again to simulate this differentiation of the planet. And we looked at how these three elements distribute between the three phases. And so, so here it is in these diagrams, I show the partitioning coefficient of the three elements between metal and silicate. So simply the ratio of the concentration in the metal over silicate. And so this as a function of oxygen fugacity. And you can see here that we have really low partition coefficients in the metal, and you can see here. So we're not expecting to see a lot of these elements in the core of Mercury. But when we consider now sulfides, so now in black, I'm showing the same ratio here, but concentration in the sulfide over silicate. And you can see that with sulfide, we're able to have significant uranium, thorium, potassium, especially uranium and thorium actually in the sulfides. And so this means that if mercury has sulfides, it is very likely that these sulfides are going to store some of these radioactive elements, right? And so now we can look at in more detail how these elements behave in sulfides by eliminating effects of pressure, temperature, and composition, and just look at the role of oxygen fugacity or FeO in the silicate. So this is what is shown here. And we have the same partition coefficient corrected for these changes of pressure, temperature, composition as a function of FeO in the silicate. So again, the more oxidized, the more on the right you're going to be, and and the more reduced, the lower this FeO silicate. And you can see here that we have a bigger slope here for uranium and thorium than potassium, which shows that we're going to have a fractionation of potassium over uranium, potassium over thorium under these reducing conditions. Because of the slope here, uranium and thorium are not going to be distributed within the sulfides in the same way than potassium. And so this is actually going to fractionate in these ratios. Okay, so now we can use this data to calculate how much these elements are going to be within the core mantle and sulfide of mercury, and then calculate the bulk planetary ratios. So this is what we have here. So we use the mass balance calculation model to calculate the bulk planet, potassium, uranium, and potassium, thorium, knowing that some elements are going to be in the sulfide phase. And what you see here is that here, what I'm showing is the bulk ratios, but as a function of the mass fraction of the sulfide layer. So the fraction of the sulfide relative to the mass of the whole planet. So up to from 0 to 15.15, so 15% of the mass, which corresponds to about 119 kilometer thick layer. And so this is shown with these colored points here, with different oxygen fugacities, with the more reduced the models shown in yellow here. And these are compared with the surface with the thick black line. And you can see that if we don't have any sulfide layer, so mass fraction would be 0, the surface value and the bulk planet would be the same because these elements are very low, have very low concentration in the core. But if we have a sulfide layer, they will actually affect these ratios. And you can see that the thicker the layer, the lower these ratios are going to be, because we have more uranium and thorium in the sulfide layer compared to potassium. Okay, and so we can compare them to other planets. So you see here I have dashed lines for Venus, Earth, and Mars. And you can see that for potassium over uranium ratio, we can more easily reach the values for Venus. See, especially for this very reducing model here, with the sulfide layer of 10% the mass of the planet, we reach the Venus value. But for potassium thorium, we can only reach the value for Venus here if the sulfide layer is thick, so representing this 190 kilometer thick sulfide layer. So now if we take this data and consider just 2 N-member models, so I'm going to consider a sulfide-free mercury and a mercury with this thick layer of sulfide at very reducing conditions, minus 5.5. And we actually can report that in this diagram. So this is the same one as I showed earlier, the black diagram with the planets. So see heliocentric distance x-axis. But then I'm showing not only potassium thorium, but also potassium uranium with the chondrites at the very high end here. And I'm showing bulk silicate for Earth and Mars, since we have data from rocks of mantle and crust. And for Mars, it's for meteorites, but we have models for these planet mantle compositions. And I have surface data for Venus from Soviet landers. And for Mercury, these are the triangle here shows the surface ratios measured by messenger spacecraft. So you can see that for potassium thorium, it is the same as Mars, but it's lower for potassium uranium. So now if I'm gonna show here the bulk composition for Mercury, so including core, mantle, crust, and also maybe a sulfide layer. So this first model here with this red square, that's just with no sulfur, just core and mantle crust. And you can see that it actually shows the same values for the surface. But now if I consider this thick FES layer at very reducing conditions, it actually drops to these lower potassium thorium ratio. And you can see that we have some kind of a trend. The trend we originally predicted actually works fine for potassium uranium, but for potassium thorium, we have still a bulk ratio that is the same as Venus and Earth, but lower than Mars. And so if Mercury is very reduced, formed at IW minus 5.5 or lower, with a sulfide layer, we would have ratios similar to Venus and Mars and Earth, sorry. And so it could be as depleted in moderately volatile as Earth and Venus, and Mars would remain the most enriched terrestrial planet in moderately volatile because, as you can see here, Mars ratios would still be the highest with this black model here where we have sulfides. So Mars would be the most enriched terrestrial planet in moderately volatiles. So, I'm going to put this now in this sketch, concept sketch here, where we saw that the oxidation state for the solar system, and we can see that it increases with the heliocentric distance. And now for moderately volatile elements, we saw that Mars is the most enriched volatile planet, rocky planet. And Venus and Earth have less of that potassium, so more depleted in potassium and volatile elements. But now for Mercury, it could be as much as enriched as Mars or as depleted than Earth and Venus. They really depend on the oxidation state. So we need to have better constraint on oxygen fugacity for Mercury and also know whether we have sulfides in the interior. So it's going to depend on these two things. So better understanding the structure of Mercury, the internal structure and composition of Mercury, as well as oxidation state, would really help with addressing this problem for moderately volatiles. Okay, so now I'm going to start addressing this other question. Are planetary building blocks in the inner solar system like enstatite chondrites, especially if Mercury is like enstatite chondrites in composition? So you saw this Urey-Craig diagram I showed earlier. So if I want to report Mercury in here, I have this big range for FESI. So the diagram on the right is actually a zoom out of the diagram on the left. So you see everything squeezed here at the bottom for the rest of the planets and chondrites. And so Mercury has this big range of composition because of silicon being in the core, actually. So if you have a lot of silicon in Mercury's core, you would sit here at the bottom with other planets and chondrites. But if you don't have silicon in the core, then you would have higher iron silicon for the planet here. And so in any ways, Mercury, you can see that it is very reduced again, actually as reduced as enstatite chondrites here in terms of iron oxide versus iron metal proportions. And so you can see here that actually this is why we're motivated with this question here, whether Mercury can be formed with this type of chondrite, enstatite chondrites. So what we do to answer this question is we use data from MESSENGER. So MESSENGER, the spacecraft that orbited Mercury, had an X-ray fluorescence, X-ray spectrometer that was able to measure the surface composition using X-ray fluorescence. And these were induced by solar X-rays exciting the surface of mercury. And so it's really great because we can do a lot of geochemistry with that. Just because of mercury being so close to the sun, we have a lot of X-ray fluorescence happening. And actually, the mission messenger was actually provided these maps of the surface composition, not for all elements, computed for all elements. It is computed for magnesium, aluminum, over silicon ratios, but for elements like calcium that need a lot more energy to excite, we have incomplete maps, especially in the north. Here, we didn't have enough of those high energetic solar winds to have to measure calcium. But so now we're still with this data, we're able to test whether mercury can be formed in enstatite chondrites by performing experiments at high pressure and temperature and look at the melting products of enstatite chondrites and comparing them with mercury. And so this is what we've been doing. We just considered enstatite chondrite, EH4, and we considered more reducing conditions than enstatite chondrites by reducing the silica. As much as the original chondrite has about 62% silica, we dropped that silica content in order to include some of it in the metal phase. So with having this 12% in the metal. And so by doing that, we also increase the fraction of metal and sulfide over silicate from 40% to 50%. And this 12% silicon in the metal is actually in agreement with results on mercury's core composition, constrained from the gravitational field of mercury. You can see that 12% is close to the median value for models for mercury's core composition and silicon fraction. And we conduct experiments at pressures spanning the whole range of mantle pressures, from the crust mantle boundary to the core mantle boundary, and at very low oxygen fugacity because mercury is reduced, so approximately -5 to -3. And we compared our results with PMES modeling, the software that enables to look at magmatic fractionation for equilibrium melting and sulfur-free conditions and less reducing conditions are oxygen fugacity of RW close to RW buffer. That's just what PMES can do. It cannot actually take into account of reducing sulfides and this low oxygen fugacity. So that actually gives us an opportunity to compare what mercury melting products for enstatite chondrites would look like if we have slightly more oxidizing conditions and no sulfur in the system. And then we compare our results with surface composition of mercury. So these are the kind of samples that we have. We have samples that were heated at higher temperatures and other lower temperatures. And so we have metal, nickel, silicon phase, silicate melt, orthopyrexene, and a little bit of olivine for a few samples, only 0.5 gigapascal, as well as some sulfide phases. And so samples that have sulfides were run at lower to moderate temperatures. And for solid phases, we have silicate solid phases that show, especially orthopyrexene, showing euhedral to subhedral textures with different sizes. And finally, the silicate melt here shows some dendritic texture, which is typical of high pressure samples due to the quench fast, and which just doesn't allow us to have glassy textures. It's very typical of high pressure samples. Okay, and so we have sulfides actually that have up to 22 weight% magnesium and 13 weight% calcium. And you can see here that these sulfides are different than the one I showed in the previous work, with FES. So now we have magnesium and calcium, and we do find these kind of sulfides in enstatite chondrites and enstatite achondrites, chondrites. And so the question here is, under what condition do we have these calcium and magnesium-rich sulfides? And so with the data that we have, we were able to just plot this distribution of calcium and magnesium between sulfide and silicate, and plot it as a function of things like temperature and oxygen fugacity shown with color here, as well as a silica concentration in the silicate met. And what we see here is that when we have moderately reducing conditions, that's when we have more calcium and magnesium in the sulfide, surprisingly. And also at low temperature, we have higher magnesium concentration in the sulfide and a higher silica in the silicate met. We have more calcium in the sulfide phase. And so these are the two equations that actually summarize this. So at moderate oxygen fugacity, low temperature, and high silica in the silicate met, we are more likely to have these magnesium and calcium-bearing sulfides. Okay, so now we can look at the silicate met compositions, and they're shown here as a function of the degree of melting. And we see some typical trends like compatible elements, magnesium concentration increasing with the degree of melting, while incompatible elements like aluminum, oxygen, potassium, their abundances decrease with the degree of melting. And for calcium, silica, and sulfur, so these are more complex here. We see, for example, for sulfur, for our silicate mets, we have up to 13 weight% sulfur in the silicate met. And so we understand this actually sulfur replaces some of the oxygen as an anion, S2-, and 13 weight% sulfur represents approximately 10 atoms of oxygen. So out of 10%, out of all the oxygen, we can have up to 10% of this oxygen being replaced as sulfur, which is really huge. And so this actually, we're going to see here that it's really important in for equilibrium happening during mantle crust differentiation for Mercury. And we also see that we have some correlation between sulfur, calcium, and silica. And so these are also very interesting. So now to better actually understand what's going on with our silicate met compositions, we report them in pseudo-ternary diagrams. And so these are actually diagrams with forced right, chords and members, and also calcium chermak. So calcium chermak is this end member between alumina and wollastonite. And so on the left, I'm showing results for low pressures, and on the right, higher pressures. And I reported also liquidus boundaries for calcium, magnesium, aluminum, silica, as well as calcium, magnesium, aluminum, iron, silica systems at different pressures. And if you don't remember how this works, if you follow the arrows, you fall into the eutectic. So lower temperatures are going to be here, and higher temperatures are going to be at the edges of the diagrams here. And also, if you have a composition that is like in this field, for example, quartz, it means that you have this quartz or polymorph of SiO2 in equilibrium with your silicate met. And if I'm in this field here where I have enstatite, it means that my silicate met is in equilibrium with enstatite. Okay, so our starting composition is this ellipse here in white. And now I'm going to report met compositions from METs and PMETs modeling. And so these are the composition of the partial METs that I would get from equilibrium melting at the different pressures. And you can see that actually they don't really follow these liquidus boundaries. So for example, here, on the left here, you can see that I have compositions are slightly to the right to these liquidus boundaries, and so this is because our composition is not pure CMAS or CMFAS. We have also alkalis, and it's been shown in the past that actually these are going to affect as much as titanium. Other things than these elements are going to actually shift these liquidus boundaries, and that's why we don't have them fit in here. These boundaries. And so now I'm going to report composition of our experimental METs. So these shown with colors here, again, low pressure on the left and high pressure on the right. And you can see here that our experiments shown with these squares here do not fall within these PMETs predictions. And especially on the left here, you can see that the high temperature METs are going like from the starting composition to the other opposite side of enstatite, it's because we have enstatite that is a lot more stable than in PMEDS models. And you see here, PMEDS actually have MEDS are the opposite side of forsterite, and that's because of how these actually have olivine present in equilibrium with the silicate MED. And so this really our results show that we have enstatite a lot more stable than with PMS models. So all samples have enstatite, and only olivine is only stable at 0.5 gigapascal. And so this, I'm going to talk more about enstatite, why we have this enstatite stability of enstatite being more stable in these conditions. But that is one observation, is that enstatite is a lot more stable in these reducing conditions and high sulfur content. Also, the MEDs produced at high temperature and low pressure have a higher magnesium over silicon ratio than PMS projections. And so these are the points that I showed here at high temperature. We have a lot more magnesium in the MEDs than in PMS, and that is also related to olivine not being stable. And finally, at the low temperature here experiments, we have a large range of compositions, and that is due to the presence of sulfides, because these are the conditions that actually allow these calcium and magnesium-rich sulfides to be stable. And so because of this calcium and magnesium being within the sulfide phase, we have different compositions, and so that affect actually the silicate MED composition. And so now enstatite is more stable in our experiments due to the high sulfur concentration in silicate MEDs, which actually prevents having enough magnesium oxygen bonds in the silicate MED, and that prevents olivine from crystallizing from the silicate MED. And so actually we think that is because of the decrease of MgO activity in the silicate MED relative to SiO2 that enables us to have more enstatite stable than olivine. And it can be shown with this reaction, olivine with sulfur. A lot of sulfur in the system actually forms MgS and orthopyroxene. And so this result is in agreement with the recent study by Enriched et al. That showed from using Xenos data that sulfur bonds with magnesium here at low oxygen fugacity within the silicate MED, as well as calcium at more radioactive fugacity, and so this just shows that within the silicate MED, we have MgS and CAS moieties, and these prevent olivine. So phases are rich in magnesium, but also we expect calcium-rich phases like dioxide to be stable at the expense of enstatite. Okay, so now we can compare our compositions with Mercury's data, surface composition. So do we have similar compositions, those seen on the surface? And we see that we have a nice overlap here. These crosses in gray show Mercury's surface composition. So we have a lot of overlap. And also in the total alkali SiO2 diagram, we also see overlap with Mercury's surface shown with this gray field. And now we can use this data to compare directly with maps. And what we did is look at each pixel of the maps and see what is the silicate MED that matches the best with those compositions, and what are their pressures and degrees of melting. And we were able to produce these maps here that show the pressure and degree of melting of MEDs produced in the lab that match the best with the surface composition of Mercury. And you can see here that we have a big range of pressures from 0.5 to 5 gigapascal, and degrees of melting that also can range large range, but mainly between 25 and 5% degrees of melting, 10, 25. Okay, so and what we see here in detail is the northern volcanic plains in the north here, and the Caloris Basin suggests melting at the shallow depths, 40 to 80 kilometers, and a high magnesium region here. This area suggests melting at very high pressures. 5 gigapascal represents actually the core mantle boundary, so we might have some melting down to the core mantle boundary, and we also have regions here that might be forming at deep in the mantle, but not down to the core mantle boundary around gigapascal, corresponding to 240 kilometers in areas here shown in green in the top diagram. So we also consider whether these MEVs can be produced by, the compositions on Mercury can be produced by mixing due to, for example, impact gardening. So taking like samples from different areas and spreading them around across the surface of Mercury. If we have magma also mixing within different magma chambers. So yeah, and so what we do is just test whether taking two silicate MEVs mixed together, we can match better the surface composition. And we do actually, and this would actually give you the first MEVs produce a high pressure up to 5 gigapascal in more areas than the previous direct comparison model. And now, how well do our MEVs fit with Mercury? So to do that, we now just compare, you can see it visually here, Mercury messenger data, so the surface composition of Mercury compared with our experiments. So for the mixing model here, and you can see that for magnesium and calcium over silica, we have good match here. But for alumina, there are many areas here, like the high magnesium terrain, but also calories and places around it, and the southern hemisphere that have lower aluminum in our experiments than the surface compositions here. So yeah, all these areas here have a lot more aluminum, but the rest works well. And so this suggests that maybe these areas may be forming with more complex differentiation processes and possibly with the presence of feldspar in the source mantles for the source melting for these surface areas. Okay, so we just saw here that we have some good match, but with exception of some surface areas are enriched in alumina. And so our model here for enstatite chondrite works well. However, one thing that I didn't mention, and I want to actually emphasize here, is that our model here, we were able to increase the metal sulfide fraction to 50%, but Mercury has a higher core to mantle fraction. The actual core represents 68% in mass instead of 50%. So we do have some of the iron, more iron, silicon, nickel in Mercury than what we see in our experiments. And so this can be explained with the impact that might have stripped the mantle of Mercury. So this just shows that for the surface composition, the silicate MEVs on Mercury can match Mercury's partial MEVs. However, the bulk composition, for the bulk composition, we need to consider impact that may have stripped some of the mantle and increase the mass fraction of the core. Okay, so now adding to our concept sketch here, and so you can see that mantle geochemistry, I'm going to add constraint from this geochemistry. So enstatite chondrites for Mercury, it works okay, but impact would be needed to increase the mass fraction of the core. So now I'm going to very quickly talk about other planets for geochemistry here. What about Earth and Mars, for example? And so Earth has a very similar isotopic composition as enstatite chondrites. And so you can see a very good match between enriched chondrites with Earth and the Moon. Here for many isotopes like titanium, chromium, nickel, oxygen, molybdenum, neodymium, but also elements I'm not going to show here. And for Mars, so this suggests that, this suggests that Earth and Mars may be forming with the similar materials, have common building blocks. But for Mars, actually, this isotopic composition for Mars suggests a mixing between enstatite chondrites and ordinary chondrites, something like 75% enstatite chondrites and 25%. And actually, if we look at more titanium and chromium isotopes, for example, we see that we have two reservoirs in the solar system for isotopes, so non-carbonaceous chondrites and carbonaceous chondrites. But anyway, so it looks like the rocky planets, Mars, Earth, and also the Moon, may be forming from non-carbonaceous chondrites, and for Earth, something like enstatite chondrites. So for isotopes here, both Earth and Mars show that they form in majority with enstatite chondrite, but Mars also has something like 25% ordinary chondrites. forming something like a mix of the two. And so for Mars and Mercury, unfortunately, we don't have samples. So it would be really great to have samples from these planets to be able to measure isotopes and have better constraint about compositions of the planets. But now the thing is for Earth composition, even if the isotopic compositions are very similar for Earth and enstatite chondrites, the mantle composition for Earth is actually very different than enstatite chondrites, especially it is more enriched in aluminum and magnesium and more depleted in silica. And even if you include some silicon in the core of Earth, we don't reach this composition here. So this might mean that we have an incomplete sampling in the nebula or other processes affected the composition of the building blocks. And I don't have enough time to talk about this, unfortunately, next time. So anyway, so Earth may be formed with meteorites that are not sampled and not identical to enstatite chondrites in composition. And so now this really cool diagram, if anybody wants to like look at all the data from different planets, I recommend you looking at this paper where you can see plotted in the same diagram here other compositions like Venus, Mars, or the Moon. Okay, so to conclude here, both rocky planets and asteroids show a gradient oxidation state in the inner solar system. We might have a gradient on volatile elements, but we need to have better constraint on Mercury's internal structure and oxygen fugacity. Isotopic composition for Earth and Mars suggests the formation of enstatite chondrites, mainly, but also ordinary chondrites. And Mercury's mantle is similar to enstatite chondrite, might be similar to enstatite chondrites in the surface, or especially that would explain surface composition. However, there are some complex differentiation processes that would need to be taken into account to better have a knowledge, better constrain the mantle composition. And finally, Earth mantle is enriched in aluminum and more depleted in silica and enstatite chondrites, suggesting that maybe we don't have enough samples from early chondrite-like primitive materials in the inner solar system. Yeah, so thank you.
All right, thank you, Asmaa. It's a very nice talk.
5 minutes questions. Thank you. Yeah, I can take 5 minutes questions and be at my class.
Okay, so yeah, if you guys have any question, please raise hand and I'll allow you to speak. So if do you have any question to Asmaa? Okay, then there is a question in a Q&A from Dr. Ampomier, and I will read it. Thank you for very interesting talk. The role of sulfur on silicate metal composition is likely influenced by Si bonds, not just MgCas. So significant portion of S bonds with Si, as evidenced using the Si-NMR spectroscopy by Pommier et al. 2023, and recently confirmed by Fisher et al. And these bonds could explain the viscosity of the reduced melt, as measured by Morsel et al. According to you, how do you S bonds in the melt affect the stability field of enstatite?
Yeah, thank you for this question. Very good question. So thank you, Anne. And so Anne, she used NMR for silicon NMR, and they found that there is also SIS bonds. And so, yeah, there might be not only MgS and CAS bonds, but also SIS. And so what I'm going to say is that, yeah, for example, for calcium, we do see that silica in the silicate melt affects the distribution for calcium between sulfide and silicate. So there is something that's going on also with silicon. And so the thing is that we might still have more MgS and CAS bonds than SIS. Otherwise, we wouldn't have this stability, expansion of this stability of enstatite, right? So if we have more SIS bonds than MgS, then we would not have this increased stability of enstatite. So the thing is like right now, it would be really nice to quantify this, like how much of these SIS bonds versus MgS bonds to better answer this question. But the fact that enstatite is more stable over olivine suggests that we might have more MgS and SIS. That's all I can say for now.
Okay. Asma, do you still have time?
Yes, I have 2 minutes.
Okay. So there's another question from the Q&A. Kathleen Frizel. Okay, I read it. Great talk, thanks. If you were able to send a surface mission to Mercury, where would you want to send it? And what science instruments would you want to include?
Yeah, very good question. Maybe I can show this one here. So it's Mercury. We're not like, I know that people are interested in life, so Mars, but I would say like, so if, for example, if you wanna make Mercury more sexy, you would like go to the HMR here, where you have 5 gigapascal. But we found that maybe we have mesform at 5 gigapascal because a paper recently suggested that we might have a layer of diamond between core and mantle. And it was published last year in Nature Astronomy, I think. And so if you have mess that came from that deep at the core mantle boundary, maybe we might have something from some diamonds there. I don't know, possibly. Anyway, and so that would be just cool for everyone to just hear about diamonds on the surface of the planet. Otherwise, also this area would be really nice because that's where you have a lot of this HMR, this high magnesium region. In the past, it's been argued to have been formed due to an impact, a large impact that just mantle all the way to the core mantle boundary, but it's very it's not really sure so far. It's very controversial because we don't have features at the surface, geomorphologic features that would suggest that we had such a big impact. And so it would be nice maybe to go to the western part here where you have a contact between this deep mantle stuff and mess formed at lower depths, like the northern volcanic plains here. Yeah, going here, like sending a rover here would be nice. But that's for the geochemistry, like mantle cross differentiation. Someone like me is interested there, but there are some other cool things you can do on Mercury. For example, in some permanently shadowed craters, there are some ices that we found there. Messenger found ices there, so that's also really cool stuff. Like just to see what kind of ices are there. Like, is it organics or water ice? And and like, do they come from comets or things are older than that? All these questions are really interesting. And so, yeah. Thank you for this question. Unfortunately, I have to go because it's 1 now.
Yeah, it's already 1. Yeah.
Yeah. Okay. Thank you very much.
Okay. Thank you very much for coming, and thank you very much for your nice talk, Asmaa.
Thank you.
Right. Thank you, and yeah. Goodbye. Bye.
Bye bye.